Uh, Good afternoon, everyone. Today, I'll be presenting a review of a decade of research on handling imbalanced medical datasets. We will explore the various techniques and advancements made uh, over the past 10 years. Okay, so in the medical field, machine learning is increasingly used to assist in diagnosis. However, medical data often has the problem of imbalance, meaning that cases of certain disease are far fewer than those of healthy individuals. This imbalance can lead to machine learning models performing poorly when predicting rare disease and high cost of misdiagnosing disease individuals. Models favor majority class, neglecting minority class. It severely impacts machine learning models' performance. Therefore, how to deal with the imbalance problem in medical data is an important research topic. So this report will review the research on handling this problem in the past decade, from 2013 to 2023. Identify effective methods and look forward to future directions. So, how is class imbalance defined? It refers to a situation in a data set where the number of instances across different classes is disproportionate, proportionate, uh, typically with the majority class having a significantly more samples than the minority class. So, the imbalance ratio (IR) is defined as the ratio of the number of instances in the majority class to the number of instances in the minority class. The larger the ratio is than 1, the more severe in the imbalance. So the research background and the motivation. Class imbalance refers to the large difference in the number of samples of different categories in the dataset. For example, in a heart disease dataset, healthy people may far outnumber those with the disease. When the machine learning models are trained on this imbalanced data, they tend to predict the majority class and ignore the minority class. So in the medical diagnosis, the minority class, like the diseased people, is often what we care more about. If the model cannot accurately predict the minority class, it may lead to delayed diagnosis and missed treatment opportunities. Therefore, we need to find some effective methods to balance the data or adjust the model to make it more focused on the minority class. So the purpose of this study is to systematically analyze existing methods and evaluate their performance on different medical data sets. So what's our research questions? In this paper, first one is framework for classifying and evaluating imbalanced learning techniques. And the second is emerging trends and future direction in handling imbalanced medical data. And the third, uh, methodological recommendations to mitigate class imbalance. And to find relevant research, we search in the two databases of Google Scholar and Scopus using specific keywords. The main keywords include imbalanced and medical to ensure that we find medical data related to the research dealing with class imbalance problems. To ensure that the found literature is relevant to the topic, we also excluded some common keywords such as diagnosis. And the search scope is limited to literature published between 2013 to 2023 in January 14. So the figure 1 and figure 2 literature search flow chart illustrate how we selected 137 papers for analysis from the hundreds of papers initially found. And this is the keywords. So after removing duplicates, screening titles and abstracts, and for reading, we finally select 137 papers for analysis. Okay, so the medical dataset and evaluation metrics, the figure 3 and figure 4 show non-reference and reference class imbalanced medical datasets. Figure 3 shows the publicly available medical datasets that were used less frequently in the literature reviewed by the researchers. So you can see many different datasets named on the figure, such as arrhythmia, thyroid disease, and so on. The bar next to each dataset name represents how many papers use that specific dataset. The longer the bar, the more frequently it was used. But compared to the figure 4, these datasets were used relatively less often. The figure 4 is the reference class imbalanced medical datasets. The figure is similar to the figure 3, but it lists the reference datasets that were used more frequently by researchers when studying the problem of class imbalance in medical data. Again, you can see many datasets names such as breast cancer, Wisconsin, heart disease, Pima Indians, diabetes, and so on. The bar next to each name also represents the frequency of use, and you can see that the bars for these data sets are generally longer than those in figure 3. It indicates that they are more common benchmark data sets in this file. Okay, so the imbalance ratio refers to the ratio of number of majority class samples to the number of minority class samples, which is used to measure the degree of data imbalance. And the table 1 is the description of reference class imbalance medical data sets. This table is table 1. So this table provides the detailed description of the reference medical data sets list in figure 4. For each data set, the table tells you the total number of instances, the number of features, and the number of data points in the minority class, like sick people, and the number of data points in the majority class, like health people, the total number of class, and most importantly, the imbalance ratio. For example, the imbalance ratio of the cervical cancer dataset is as high as 14.6 to 1. A larger ratio indicates a higher degree of imbalance in the dataset. Additionally, they observed an underrepresentation of certain medical domains like psychiatry and psychology, possibly due to data scarcity or the fact that the data in these files is often unstructured, which falls outside the primary scope of their structured data analysis. And the evaluation metrics when evaluating the performance of a model on imbalanced data, it is not enough to look only at accuracy, and other metrics need to be considered. First one, accuracy is the overall percentage of correct predictions, and sensitivity is the percentage of correctly predicting the minority class. It means the disease. So the third is the specificity is the percentage of correctly predicting the majority class. It means the healthy people. And the geometric mean. The geometric mean of sensitivity and specificity. And F1 score, the harmonic mean of precision and recall. And the final is the AUC, is area under the curve. The area under the curve used to measure the model's ability to distinguish between different categories. Sensitivity and specificity are particularly important in medical diagnosis because they are directly related to the accuracy of diagnosis. So this is the figure 5 and table 2. They illustrate commonly used and less commonly used evaluation metrics. Figure 5 shows the most frequently used evaluation metrics when researchers study the problem of class imbalance in medical data. These metrics are used to judge how well their proposed methods perform in the disease prediction. So you can see the different metrics names on the figure 5, such as AUC, ROC. Recall is mean sensitivity and accuracy and F1 score and so on. The bar next to each metric represents the percentage of papers that use these metrics to evaluate their models. So you can see that recall and accuracy are among the most frequently used. And the right table is the table 2. The table 2 is in compared to the commonly used metrics in figure 5. This table lists the evaluation metrics and statistical tests that were used less frequently in the literature they reviewed. The table has two columns. One is for usage frequency and the other is for the specific metric or test name, such as Hamming, Lowe's, ANOVA, Markov F1, and so on. So the methods for handling imbalanced data. There are three main methods for handling imbalanced medical data are discussed in this paper. The first is the pre-processing methods, and the second is learning level methods, and final is combined techniques. So the first one, feature selection. Feature selection can improve the interpretability of the model. Select the most relevant features to reduce data dimensionality. The role and the feature weighting. The role of the feature weighting can increase the model sensitivity to important features. It can assign different weights to different features. And the third is the feature extraction. Feature extraction, especially when dealing with high dimensional data. and to reduce the dimensionality of the data, particularly when addressing the challenges of class imbalance. So the table 3 on this slide. The table 3 introduce the feature level methods that researchers use to address the class imbalance problem in medical data. Features like the different pieces of information that describe a patient, such as age, blood pressure, and so on. So this table lists the different studies with each row representing a paper and briefly explains the key idea they used and the year of publication. So the main goal of these methods is to select the most important and useful features or to adjust the weights of the feature so that machine learning models can better distinguish between different classes. And the number 2 is the data level approach. Oversampling. It can increase the number of samples in the minority class, such as using SMOT technology to synthesize new samples of the minority class. And undersampling, as the name suggests, is mainly about how to reduce the number of examples in the majority class to make the class proportions more balanced. If there are very few patients with one disease and many with another, the model might be biased towards predicting the more frequent disease. Although undersampling may lose some information, it can reduce computational complexity. And the hybrid methods can combine both oversampling and undersampling techniques, such as SMOT ENN. Undersampling involves reducing the number of samples in the majority class. So hybrid methods might first increase the number of minority class samples, and then it decrease the number of majority class samples, hoping to achieve a better balance. So the table 4 and table 5. Table 4 introduce the oversampling technique, which is a method used to handle imbalanced class. The table lists different oversampling techniques, which with each row again representing a paper and their key idea, and they propose the year of the publication. The most common oversampling technique is SMOT. The table also lists some improved versions of SMOT, such as SMOT based on the minimum spanning tree, or SMOT combined with clustering methods, and so on. And the table 5, you can see that this table lists some undersampling method proposed in the research. You can see that some methods decide which majority class samples to remove based on data clustering. For example, the methods by Raymond and Davis and Parvin in 2013, they believe that this can avoid random removal and instead strategically retain more representative majority class samples. So the table 6 introduce hybrid data label techniques. For example, some study might use mode to increase the minority class and also use random undersampling to decrease the majority class. About the learning level part, basically it means we don't change the data itself, but we try to deal with the data imbalance when we train the model. So the first cost-sensitive learning, it tells the model that misclassifying the minority class, usually sick patients, should have a higher penalty than misclassifying the majority class like healthy people. And this makes the model pay more attention to the minority class during learning. And the ensemble learning, it doesn't use just one model, but multiple models to make predictions together. These models might be trained using different methods and their results are combined uh, to improve overall performance on imbalanced data. And deep learning, it uses more complex neural networks to learn patterns in the data. While deep learning is powerful, it might face issues when there isn't enough medical data. So the right table is the table 7. The table 7 is introduce techniques that address class imbalance from the learning algorithm level instead of directly modifying the data. These methods adjust the way machine learning models learn so that they can perform better when dealing with imbalanced data. The table lists many different studies and the approach they used, including cost-sensitive learning. And this table is the table 8. Table 8 introduced combined techniques that integrate the data level methods like oversampling or undersampling feature selection, and learning level methods like adjusting algorithm discussed earlier. So the researcher have found that using a single method might have limited effectiveness. So they try to combine different techniques, hoping they can complement each other and achieve better results. For example, some studies might first use more to increase the number of minority class samples, and then train a cost-sensitive support vector machine (SVM) model. Just like this. Okay, so the research results and analysis from table 9 to 25. So from table 9 to table 25, these tables some summarize the results obtained by different research papers that use various methods to address class imbalance on the common reference medical data sets listed in the figure 4. And each table focuses on a specific data set. For example, table 9 shows the results for the breast cancer Wisconsin original dataset, and table 10 for the heart disease dataset, and so on. And for each paper, the table lists the research approach they used and their performance on different evaluation metrics such as accuracy, area under ROC curve, sensitivity, specificity, F, F value, and Gn is a geometric mean and precision and so on. The purpose of this is to compare the effectiveness of different methods on the same dataset to see which approach might be more suitable for handling the imbalance problem in that specific dataset. So for example, on the breast cancer dataset, ensemble learning and hybrid methods usually perform well. And on the heart disease dataset, cost-sensitive learning and ensemble learning have better results. So overall, no one methods performs best on all datasets, and the appropriate methods need to be selected according to the specific situation. And in addition, their study also found that feature engineering has a great impact on the performance of the model. So, the discussion is a challenge and insight in handling imbalanced medical data. Context dependency of method choice. Although many studies suggest high classification performance given the distinct specific of the datasets detailed in Table 1 and the diversity of methodology explored in the existing literature. Research findings are highly context dependent and may not be broadly applicable, so it needs cautious interpretation and an understanding of the limited scope. And studies addressing class imbalance in medical application frequently reuse the reference data sets presented in the Table 1. Assured objective for this study is the evaluation of the proposed class imbalance approach over medical data exhibiting a certain degree of imbalance. However, the research reveals a lack of specificity in how terms like diagnosis, prediction, and classification and early detection are employed interchangeably. This could be attributed to the overarching challenges of class imbalance, which seem to outweigh the need for clear differentiation in study objective. Hmm? And the transparency issues in research reporting. The literature often lacks detailed description of data sets, methodology, and experimental implementations, which limits the depth of analysis, such as sampling ratios frequently omit details like post balancing data distribution. As such, more intensive investigative approaches are needed that delve beyond mere describing to achieve a more comprehensive analysis. And the lack of a universal standard for quantifying imbalance severity, the absence of a universally accepted standard for quantifying the severity of class imbalance complicates the comparison of results across different studies and hampers the development of potentially broadly effective solutions. Establishing clear metrics are essential to facilitate a more consistent evaluation of methods' effectiveness across varied research contexts. So the future direction in the field of imbalanced data handling, we face multiple challenges, but also hold in immense potential for development. First, we need to develop automated sample partitioning standards based on data distribution to ensure objectivity and consistency in sample partition, partitioning while uh, while preserving the characteristics of the original data. And furthermore, we should actively explore the sampling techniques beyond SMOT, overcoming its drawbacks to achieve superior performance. And we need to optimize ensemble learning strategies to enhance their effectiveness on imbalanced medical data. In the medical field, model interpretability is crucial. Therefore, we should develop interpretable imbalance diagnostic models to enhance trust and adoption among healthcare profession, per, professionals. And finally, to comprehensive evaluate model performance across all classes, we need to adopt diverse performance metrics, including sensitivity, specificity, and others, rather than relying solely on general metrics like accuracy or AUC, ROC, and F1 score. So in conclusion, it's evident that handling imbalanced medical data is crucial. While the past decade has seen numerous methods proposed, each comes with its own set of pros and cons. Therefore, selecting the most appropriate method for a specific context is key to success. At the same time, pre-processing and learning level methods continue to play a central and vital role. Future research needs to define its objectives more clearly to ensure that method selection and evaluation are more targeted. Furthermore, we must emphasize that transparency in research reporting needs significant improvement to facilitate more in-depth analysis and comparison. Okay, thanks for listening.